Welcome. In this week, we're going to look at what is feedback and what is feedback control. This is as opposed to what we know or call open loop control. For example, suppose we have a target. If we shoot at it with a gun, the bullet leaves the barrel of the gun and just follows whatever prescribed path it's going to be based on how we aim the gun. Compare that to a guided missile. The guided missile uses feedback control. So the guided missile sees the target, and when it sees it's going to miss the target, it adjusts its flight path to intercept the target. So that's the kind of control systems we're describing in this class. And so that's what we're going to talk about at first, just basically an introduction to the class. The next thing we're going to be doing in this class is we're going to be using a system or a theory known as modern control theory. Modern control theory is all based on using state equations like this. X is known as the state. And for say a simple system, the state might be the angular position and the angular velocity. And those two numbers together in a 2x1 vector make the state x. X dot means the derivative of x with respect to time, or the rate of change of x with respect to time. A is a matrix. And for the simple system, it would be a 2x2 matrix. For a more complicated system, it might be many more. For example, for a drone with 4 propellers and 6 degrees of freedom, I think we calculated it was something like a 24x24 matrix. But it's the very same state equation. So we're going to be using this state equation. We're going to get familiar with this state equation, and if we can do the simple pendulum with just theta and theta dot, the rate of change of theta with respect to time, or angular velocity, then we can also do the drone with 4 motors and 6 degrees of freedom. Now, when we want to control one of these things, like, for example, this 2-wheeled cart, we need to write the equations that describe the motion of this cart. Those are known as the dynamics equations. And you could do that from Newton's laws. However, Joseph Louis Lagrange came up with actually a very nice method of doing this that takes into account all of the constraints. In other words, this thing can't do some things, like it's not going to jump up and go like this. It's going to be resting on the ground. And his equations make coming up with the dynamic equations much easier than it would be for Newton's laws. So we're going to be using that, and essentially it's the same result you would get from Newton's laws, just much easier to handle and think about and write down. We'll also apply circuits. How do we write circuit equations in the state form, in the x dot equals ax plus bu and y equals cx plus du? Now on these state equations, u is the input, x is the state, y is the output, or the things you measure. And so we're going to be using these state equations all through the class, and we need to understand them, so we'll be introduced to them in the first week. Then lastly, this set of equations is a linear set of equations. In other words, if I double u, it doubles y, it doubles x. And so why are we using linear equations? Well, linear equations are much easier to deal with than nonlinear equations. And so we want to make our equations linear if at all possible. And what we can do is we can make it linear for like small excursions. For example, on this cart right here, we have a pendulum. And if I, just give it a push, it moves. If I double the push, it actually doesn't double the angle that it goes. And you can see if it's up like this, if I give it a push, it moves like that. And it's not the same as when I gave it a push down here and it moved. So what I want to do is I want to take the equations that Lagrange gave me, and I want to turn them into an approximation for a small angle theta here, or maybe a small angle theta up here, so that I can balance this cart either down here or up here. And up here, as you can see, it's not as easy. And so that is the kind of thing that feedback and control allows us to do. So we'll learn how to linearize those equations. At the end of the week, you should be able to write state equations from a dynamic system or a circuit, and you should be able to linearize those state equations if they don't end up being linear to start with. Generally, for circuits, they're linear, but for things like this cart, they're not.